Okay, so we've been talking about momentum conservation, and in particular, momentum conservation in collisions. But in general, let's just think about, I would like to think more about this situation of when is momentum conserved, in particular in a collision. But let's just step back for a second and remind ourselves what a conservation law looks like. So we've already talked about the fact that things like force are not things that are conserved because you can exert a different force to do the exact same thing depending on what distance you move an object through, for example. But that what that brought us to was this idea that the amount of work that you have to do to move a body from one place to another place is if you have a conservative force, that amount of work is the same to get a body from one place to another place. This is just some general comments about conservation, and so that brought us to the idea of a conservative force. So, for example, if you want to move a body from point A to point B, and the only force exerted on it is the gravitational force, or anyway, any general conservative force, then it takes the same amount of work no matter how you get it from point A to point B. Yet if it's a non-conservative force, like friction, then the work is path dependent. So that gets us to the idea of what is conserved and what is not conserved. And so we can talk about such as kinetic energy. You can conserve kinetic energy. That just means that the kinetic energy, let's say, of an object, if it's conserved, that means its speed doesn't change. Or of a system, that means the total kinetic energy of the system, if you've got more than one object, right, the 1/2 MIVI squared is a constant. If we add up all the kinetic energies of all the individual particles in a system, all the individual objects or masses in a system, then if it's a constant, therefore it is conserved. So we can talk about kinetic energy conservation, and we saw that the total work on a system is equal to the change in kinetic energy. And so therefore, if no work at all is done on a system, therefore the change in kinetic energy is zero, and therefore the kinetic energy is a constant. It is conserved. Just a reminder of what it means to be conserved. We can talk about mechanical energy. Mechanical energy, ME or E, which is PE plus KE. And we saw that if the mechanical energy is conserved, and we saw that the work done by non-conservative forces, the total work done by non-conservative forces, is the change in mechanical energy. Therefore, if no work is done by non-conservative forces, so this is different than the previous one, right? If the first one was kinetic energy is conserved if there's no work on the system at all. So gravity can't do work, friction can't do work. The second one, this one, looking at this law, says if no work is done by non-conservative forces, therefore the mechanical energy is conserved. Point out that we've done this before. I've said this all before, but it's so important for you to understand and to understand the differences between when something is conserved and when it's not. Then I'm doing it again, and we'll talk about momentum in collisions and how it relates to this. I'd also ask how you remember all this. Well, the answer to that really is that these are all the same concepts, just said in different ways. So if you understand the concepts and where the definition of kinetic energy and the definition of mechanical energy comes from, then perhaps starting from the work energy theorem, you can understand the rest of this. And then, of course, there's total energy, and the total energy of a system is always conserved. Now, I guess we've got to be careful here when we're talking about either an isolated object or a system of objects. We're generally talking about a closed system, right? A closed system. So if we're talking about two cars colliding, then that is our system. If there's an external force of friction on the system, then it's not closed anymore because that friction is an external force on the system. So when we're talking about conservation, we need to talk about conservation, the conservation law within a closed system. We that's always implied. It's just not always explicitly said. Let me just reiterate this last one, right? Total energy. If mechanical energy is not conserved, if mechanical energy is not conserved, what happens is that some of that energy has to have been taken away by a non-conservative force. And that's generally, or the only situation we've seen, is where heat is generated. So if you add in the heat that's generated to the mechanical energy of a system, then the total energy is always conserved. Okay. Momentum is a different thing, right? Momentum, a different thing in the sense that it's not energy. And don't confuse momentum conservation with energy conservation. We showed that for momentum came from Newton's second law, and it came from this equation, the impulse equals the change in momentum. And so therefore it should be quite clear that if either of these, delta t or F net, is zero, then delta p is zero, right? Delta p, the change in momentum, is zero if, and only if, F net on the system is zero, or delta t is zero. You say, whoa, delta t is zero. That means no time has passed. Well, of course, the momentum hasn't changed if no time has passed. And that's true. That's true. And that's a good observation. That if no time has passed, then the momentum of the system hasn't changed. That's quite reasonable. But we do extend that. So let me just forget F net equals zero for a second. Just think about delta t equals zero. Two collisions. Say, well, if a collision... And I do often use two cars, but a collision can be between anything, right? Collision can be between two people on an athletic field. It can be between you and a door when you're walking through a swinging door. It can be, between any two things. A collision. In a collision, as long as it's an ideal collisions essentially occur in no time, right? So it's that something was going on before the collision, and then something is going on after the collision, right? Maybe these two cars had a collision and they're stuck together. And we just say that in an ideal collision, there was really no time between the before and after. That's really why we say in all collisions, momentum is conserved. We're not really taking into account whether there are any external forces, because we say there is no time for those external forces to affect the system, because delta t equals zero. So delta p equals zero for an ideal collision, because in an ideal collision, delta t equals zero. There's no time for before the collision to after the collision, right? We can talk about things that happened in the time before the collision. The collision happens instantaneously, right? That's what it means, instantaneously. And then what happens after the collision. But when we're comparing what happened right before the collision to right after the collision, delta t equals zero, so delta p equals zero, so momentum is conserved. Now that is only for an ideal collision. In real collisions, right, momentum may not be perfectly conserved from before to after. But we will always assume momentum is conserved in a collision, unless you're otherwise told. But the other time that momentum is conserved is if there is no net force on the system. If there's no net force on the system, and that's why in a collision we can say there was no time for the net force to take to impact to change the momentum. So we sort of treat it as if there's no net force on the system, but then maybe there is a net force on the system. For example, what do I mean by a net force on the system? Let's say that we're talking about a car collision, but the cars are going downhill. Cars are going downhill, and they have a collision. Is an external force on this system, and that's the external force of gravity, right? Gravity is speeding up these cars in the downhill direction, but we can still assume that momentum is conserved for the collision as long as it takes place instantaneously. But there is a net force on the system. So before the collision, they might be affected by gravity. After the collision, the momentum might change because of gravity is pulling them down the hill. But during the collision, we just assume that momentum is conserved. So according to the Newton's second law, momentum is conserved. That's what that boxed equation tells us, is momentum is conserved if the net force on the system is zero or if delta t is zero. Momentum conservation isn't just about collisions, but it's particularly interesting and useful for collisions. So momentum, right, so if I, for example, if I simply drop a ball, is the momentum of that ball conserved? The answer is no. the momentum of the ball is not conserved. How do I know that? Because the momentum, let's say initially, is mv, which is 0, m times v initial. And finally, at some later time, right, it's going to be going at some velocity. Initially, if we drop it from rest, doesn't matter whether we drop from rest or not, but mv final, I guess we don't need a subscript on m because it presumably doesn't change. And it's larger, right? It's larger than 0. It's larger than it was originally because it speeds up. So clearly, because these two are not the same, because momentum is not constant, the momentum of the ball is not conserved. A car driving down the road at constant velocity, is the momentum conserved? Yes, it is, because it's going at constant velocity, so the momentum doesn't change. Actually, let's just, while we're at this, let's just think about what about the ball and the earth. Let's say that we drop a ball. Say, is the momentum of the ball conserved? No. Let's say that we change our system. And instead, before I finish that sentence, ball by itself, right? So system of ball and earth, or system of ball by itself. System of ball by itself. Okay, so we already said that for the ball by itself, P not conserved when we drop it because it speeds up. But also we know it's not conserved, not just because we see the momentum changing, but we know there's an external force, right? There's an external force, F net on the ball is mg. Okay, what about the ball and the earth? Is the momentum conserved of the system of the ball and the earth? So the system of the ball and the earth, let me change colors and say, is momentum conserved? Well, you say, okay, well, that just says, okay, I start the ball up here at let's just say v equals 0, v initial equals 0, and v final equals v. And we know that the initial momentum of the ball is mi, vi, but the system includes the earth. So it's m ball, vi ball, m earth, vi earth. That's the initial momentum of the system. Does that momentum change? Well, we know that the momentum of the ball increases in the downward direction. What about the earth? You say, well, the earth doesn't do anything, right? I mean, the earth is this big thing that sits there. It doesn't do anything. But the fact is that actually the earth, why does the ball move towards the earth? The ball moves towards the earth because there's a gravitational attraction between the ball and the earth. So while the ball falls downward towards the earth must fall upward toward the ball. You say, baloney. Of course it doesn't. Actually, it does. It's just so imperceptibly small because the earth is so large. Right? So this is large and this is small. Because the mass of the earth is so large, the velocity of the earth traveling towards the ball is so small. So then let's look at the final. We haven't answered the question. Is the momentum of the earth ball system conserved? The final momentum is the momentum. Sorry, I keep on doing this. I keep on giving a subscript for the ball. M ball, V final ball, right, which is bigger than V initial ball in the downward direction, plus M earth, V final earth. You say, is that momentum conserved? Well, now we know that the ball's momentum has increased in the downward direction. So this is bigger than this in the downward direction. And I've claimed that this is moving upward. And so actually you might be able to argue that this is bigger than this in the upward direction. And so maybe they balance out. But we can't know because we can't measure the velocity of the earth like you can measure the velocity of the ball. Because because we're standing on the earth, because the earth is so large, whatever, we can't. But, so we have to go back to, is there a net force on the system? What is the net force on the system? Well, the ball has a gravitational force in the downward direction. So now it's the net force on the ball and the earth. The ball has a net force in the downward direction equal to mg. And by Newton's third law, the earth must have an equal and opposite force in the upward direction. So what is the net force? The net force is equal to 0. The net force on the system is equal to 0. So therefore, the initial momentum of the system it must be equal to the final momentum of the system. And so from that, we could say, oh, well, let's just say that the ball was not moving initially and the earth was not moving initially. Earth, of course, is moving, but let's just say in the frame of reference of the earth, it's not moving. Well, we know that the ball has sped up in the downward direction. The fact that there is no net force on the system, because now it's a closed system of the ball on the earth, tells us that the momentum is conserved. That tells us that the earth had to speed up in the upward direction the earth moves towards the ball. And we could figure out how much it moves towards the ball. And rather than doing some math here, let me just say that if the ball speeds up from let's just make up some numbers, 0 to 5 meters per second by the time it falls to the ground, then the earth is not going to go from 0 to 5 meters per second. It's going to go, if the ball is going 5 meters per second, let's just say VF ball was equal to 5 meters per second down. That means that VF earth from momentum conservation, you would find, is equal to not 5 meters per second up, but is equal to 5 meters per second times the mass of the ball divided by the mass of the earth up. And that's where you'd find that it's so imperceptibly small that you could never measure it. You could do that math. You could do that conservation for yourself and see if you can figure that out. What I'm trying to get here is the concept of the system. If the system is the ball by itself, its momentum is not conserved. If the system is the ball on the earth, its momentum is conserved. When we're talking about two cars that are colliding, and let's just keep them going slow so we don't have to worry about anybody getting hurt or make it crash test dummies. If one car is going that way and one car is going that way, the momentum of any one car is not conserved because its velocity will change during a collision, but the total momentum of both cars is conserved because both have a velocity change. So we can talk about a single car and its momentum, or we can talk about the system of two cars and their momentum, and there's a different result depending on what our system is, whether we're talking about one car or two cars, etc. Okay, so the concept of a system is really important here. System, if the momentum of a system is conserved, it's really important to understand that let's just say a system can be any number of bodies. It's just easier for us to talk about two bodies, one or two in a system. Three, it just gets more complicated. So if one object's momentum increases, right, if the momentum goes up, therefore the other object's momentum has to decrease in order for the momentum for the system, oh, I already said if P is conserved, if the momentum is conserved. That's actually a really, really important concept. Hopefully it's obvious, but it's a really important concept. And it's something that the movies ignore all the time, right? The movies ignore this all the time. In the movies you have, I don't know, at the very least, right, you got somebody who's shooting a gun and they don't show the recoil. But when you're shooting a gun and the momentum of the gun and the projectile that the gun is shooting, gun and bullet, must be conserved. And you give that bullet a lot of momentum in the forward direction. So the gun must receive momentum in the backwards direction. That's what recoil is conservation of momentum. And you sometimes see these scenes in the movies where they're shooting really large projectiles or something, and the projectile be going off really fast, but the person who's holding the projectile launcher doesn't feel a recoil. Watch out for those kinds of things in the movies, or even in automobile accidents when one car hits another. In the movies, sometimes, right, if let's say car 2 is sitting still and car 1 is moving, car 1 hits car 2 and car 1 sort of ricochets or comes to a stop, but car 2 doesn't do anything, right? It's not conservation of momentum, because if the momentum of one thing goes down, the momentum of another thing has to go up, or vice versa.